I'm a hydrogeologist. My motto in life is think out of the box. My name, Marcel. My experience, groundwater and soil contaminations. I'm the creator of Geo RGB, a channel of geographic information systems, GIS, geology, hydrogeology, and contamination. The purpose, the objective, the goal, the intention, the target, the desire. Share my experience and acknowledge to create points of discussion. The Geo RGB community. Promote the use of free and open source software. A free digital society. Provide technical advice to environmental companies. An opportunity for professional growth.
Hello guys and welcome back to my channel. In this occasion I'm presenting the Geostatistical Analysis course related to the creation of groundwater flow maps with Kriging Interpolation. We are going to be working with R and Rstudio for the geostatistical analysis and graph design, and with Quantum GIS for the final map edition. We are going to compare the results we get with the Geostatistical Analyst extension of ArcGIS to see how we can get the same results. However, ArcGIS is a private software, but Rstudio and Quantum GIS are open source and free software. I am going to create a series of video tutorials where you are going to learn how to create a Kriging interpolation successfully. Unfortunately, Kriging interpolation is a kind of black box where most of the people just press the button next without understanding what is the math behind the Kriging method. However, in R, there is no button for next. In these tutorials, I am going to explain with examples, step by step, the spatial analysis methodology, where I'm going to be talking about exploratory data analysis, experimental semivariogram, model semivariogram, cross-validation, Kriging interpolation, and also at the end we are going to be working with the map edition with Quantum GIS and also reporting results. This is the third video of the Geostatistical Analysis course, and today we are still talking about exploratory data analysis. At the previous video we answered the question, does the data follow a normal Gaussian distribution? And for today we are going to answer the question, is the data stationary? To answer this question, we are going to create a couple of maps. One is going to be a bubble map, another one is going to be a Voronoi map, and also we are going to create a couple of scatter plots to see if there is any trend. We are going to compare the results we get with the results we can get also using ArcMAp. Remember that if you missed the previous video, you can hit on the card located at the top right corner of your screen over here. Okay, let's go to do it. To start, let's go to talk a little bit about the Kriging interpolation method. It's going to be a very small introduction, very easy one, because we are going to extend the explanation of this concept on video 4 when we talk about the semivariogram. In this scenario, we have blue points that are representing the piezometers, and each piezometer has a different groundwater elevation. The lilac points are the points where we want to estimate the groundwater elevation. Kriging is making the assumption that as closer are the points, higher is the probability to have similar value. For example, if we take these 2 points and we take these 2 points, the first 2 has a higher probability to have similar value than the second 2, because of the distance. The distance between this point and this point is shorter than the distance between this point and this point. Based in this assumption, if we want to estimate the groundwater elevation in this point, Kriging interpolation is taking the closest neighbors to estimate the groundwater elevation in this point based on the distance between these 2 points, based on the groundwater elevation in its neighbor, and also based on the spatial correlation that we are going to see on the Semivariogram. In this case, the geostatistical spatial estimation will make the assumption that the data is stationary. But what is exactly? It means that the values around all these points are going to be pretty similar. If the value between, for example, this point with this point are pretty different, we cannot make Kriging interpolation. Also, the values over here has to be pretty similar between them, and not also between them. Even area A and area B needs to have similar values. In other words, the mean of the groundwater elevation in area A has to be pretty similar of the mean of the groundwater elevation in area B, and also in area C, D, and EDC. What happened in groundwater is that we have a hydraulic gradient in most of the cases. Then the groundwater is moving from the recharge area to the discharge area, or from areas of high pressure to areas of low pressure. Then we have a specific direction of the groundwater, and if it happens, we don't have stationary values, because the values over here are going to be different than over here because of the hydraulic gradient. In that cases, we have to identify that trend, remove that trend from the data, and work with the residuals to create the model of our Semivariogram, and also to do the Kriging interpolation with the residuals. And then at the end, we can add our trend to the Kriging interpolation. In this video, we are going to see how we identify that trend with several graphs with Rstudio and also with ArcMAp. What we are going to do now is a bubble map, but at the geostatistical analysis extension of ArcMAp, there is no the possibility to create a bubble map with these options. I'm pretty sure you can do with different tools, but I'm not going to do it. I'm going to do it with Rstudio. Then just paste over here. Going to fix this one a little bit. Let's go to run. As you can see here, the first part is related where is the data. In this case, it's over here, and also we want to plot x and y. And the second part of this script is for the points, the color, what parameter we want to add to the graph is going to be the groundwater, and also what color we want for the points. The next part is for the labels of this graph, and these 2 last parts is just to make some additions on the title and also add the x's. Let's go to run all together. And now let's go to copy this one and paste over here to make some draws. Let's see what kind of information we can see in this bubble map. First, we have the coordinates. As you can see, the difference between these points is 100 meters. Then we can make an idea about the dimensions of the site. In this direction, we have around 250 meters, and in this direction, we have around 350 meters. Then also the bubble map is really good to identify the trend. As you can see, according to the license, the highest values are in this area, and here in this area we'll have the lowest values. Then the trend direction is in this direction, and it is going to help us to identify that the values are not stationary. Also, the bubble diagram is really good to identify outliers just with a glance. For example, if we have a point like this one here, it's pretty easy to recognize that we have a weird value just with a glance, right? This value, it's something weird here, and this one is something weird. And if it happens, we have to make a study what's going on there. It is pretty normal to have outliers when we have a lot of piezometers. It can happen a lot of things. For example, a technical error. The person who is taking the measurements of the groundwater can make a mistake. Also, it could be something wrong with the probe, with the instrumentation. Could be a mistake when they are taking the field notes. Could be something wrong with the construction of the piezometer. Could be that for example, the screen of the piezometer is a screen in a different depth and it's a different aquifer, or other walls are screened in a different geological layers. You know, the possibilities could be a lot, and it could be one video to try to explain how many things can happen. Now let's go to see what kind of information we can get with the Voronoi map. Go here, explore data, Voronoi map. Then here select the parameters you want to analyze. Is going to be groundwater, and here, as you can see, you can take the legend out over here, and also you can put different parameters here: simple, mean, mode, cluster, entropy, median, standard deviation, and IQR. There are a lot of parameters that you can put here, and also you can change the color of the ramp. That it's a really good tool, and you can make a lot of different things. In Rstudio, we are going to do the Voronoi map just for the simple one, and we are going to see what kind of information we can get from this map. Going to paste the code in. Going to fix this one a little bit. In this case, before to start, we have to install a lot of libraries. Going to fix also this one. Here you have the notes for each library. Okay, let's go step by step. Here, as you can see, we are going to transform the variable 8 in a spatial point data frame. As you can see now here that it's just a data frame. Now we are going to convert or transform this data to a spatial data frame with this script here. As you can see, now it changed, and we are going to see the class spatial point data frame. These scripts are related already with the Voronoi map. As you can see, the Voronoi map is already created, and the kind of file is a class spatial polygons data frame. Let's go to create a very simple map, but that map is not the one we are going to use because this one is quite simple. We can add also the points here that it represents our piezometers, but now we are going to do the graph of the map with QGplot. Then we have to run this library, also this one, and now we can work with the script. This one is a little bit more complex. I created a first object that it's equal of all this one. Then I added 2 more sections for this script. Okay, let's go to run first this one all together, and now let's go to run the second part where we are going to create the map. Now we are going to analyze what kind of information we can get from here. going to copy this one and I'm going to paste. In this map again we have the UTM coordinates, and also we have a legend related with the groundwater elevation. The red points are our piezometers, and these polygons are the descent polygons. This map is also really good to identify a trend. As you can see, it's very easy to recognize that there is a trend. Then we can say that it's good to identify if our values are stationary or not. Also, this map is really good to recognize the homogeneity of the samples. We can make a delineation of our area over here, for example. And then we have to look for the area of the polygons. As you can see, the polygons more or less has the same size. That indicates that the samples are pretty homogeneous because we have the same area for the polygons approximately. Here the density of the sample is bigger and here is lower. But more or less all the polygons has a pretty similar area, and that indicates that the location of the piezometers it's pretty homogeneous. Also, with these polygons we can show the area of influence of each piezometer. Again, in this case we can say that the groundwater flow direction is something like that. As you can see, the colors are changing, right? More or less like this. Now let's go to move on the trend analysis with some scaterplot graphs. ArcMAp has a very interesting tool to do the trend analysis. Is this option here. This is just a 3D interpretation of our data. Let's go to select the parameter we want to analyze is groundwater. And then here let's go to select this option. And if we want to move the graph, let's go to make the input data points bigger. And we can change also the color. Let's go to make a red color, for example. And if we move the graph, you are going to see a 3D interpretation of our data. That's the groundwater elevation, and each stick is the piezometer. Then we don't want this data to analyze the trend analysis. Then let's go to take out, and also let's go to take out the sticks. The information we want to see is the projected data. The data then is projected in a plane as defined here, y and zeta plane and zeta and x plane. That's the information we want to see. Then let's go to make the points bigger to see clear the information. And first let's go to work with the x and z plane. And with this option, trend of projection, we can see what is the polynomial fits better with our data points. For the x and zeta plane, the better polynomial is a polynomial of first order, as you can see, because it is a straight line. And for the plane for the y and z, let's go to move a little bit. The better polynomial, it's a polynomial of second order. As you can see, it's like a kind of curve. Now let's go to see how we can make these interpretations with Rstudio. First, I'm going to paste here the script, and I'm going to fix all this one a little bit. In this section for trend analysis, we have a couple of scatter plot graphs. One is going to be for representing the relation between the groundwater and the X coordinates, and the next one is going to be for the groundwater and the relation with the coordinate Y. In this case, the dependable variable is going to be the groundwater, and the independable variable is going to be the X and Y coordinates. In this script, for the first part, we have the frame of the graph, where we have X over here and groundwater over here. And what we are going to do is, with the data points for X and groundwater, we are going to fit a polynomial of first order, also a polynomial of second order, and also a polynomial of third order. And then we are going to see what is the best fit in the graph. For the rest of the coding, it's just some additions for the title and for the axis. Let's go to run all this script. Let's go to make zoom here, and now let's go to copy this one, and let's go to paste on here. I did already. We have the graph over here. As you can see here at the legend, we have a red color for the first order, we have a blue color for the second order, and green color for the third order. And as you can see, there is no too much differences. And what I'm going to say here, the first order is the best for this scatter plot. The trend, it's pretty evident, as you can see the points, and also for the linear regression. Now let's go to see what happened with the Y coordinates and groundwater elevation. Let's go to run the second script. In this case, the situation is a little bit different. Let's go to copy and paste. In this case, the differences are obvious. For the first order, we have the red line. And for the second and third order, we have the blue and green lines. The second and third order are pretty similar. And in this case, I'm going to say, as we saw at the ArcMAp, that the second order is the one the polynomial who fits better the data points, but also the first order, it's not really bad. What it is pretty evident is the trend of the data, as we saw also in the trend analysis with ArcMAp. However, we have to be aware that the trend, it's not in the Y coordinates, and also it's not on the X coordinates. As we saw the other day on the map, let me show you here. The trend is in this direction or something like that, with a small curve here maybe. We are going to see when we make the Kriging interpolation what is the exactly direction. But just to say something approximately, the groundwater is moving from the northwest to the southeast. Now let's go to see a couple of scripts to do a 3D interpretation of our data points. I'm going to paste over here. Let's go to run the libraries first. In this case, we have this 3D model with the Y and X coordinates, and also for the groundwater elevation at the Z axis. And the goal of this graph is just to see a little bit the trend of the data in a 3D model. The other model I believe is better. Let's go to run the other one. The other one is this one. And this one is more nice because we can move that one on the space. And just to see how the data points has that trend right at the space, that it's pretty obvious. At the end, all these graphs give us more or less the same kind of information. It's just to see that there is a trend and that trend is pretty obvious. The scatter plots, it's really good because we can know what kind of trend we have, because the regression lines maybe fit better with a polynomial of first, second or third order. But for the bubble diagram and also for the Voronoi map, we have approximately the same information. It's a little bit redundant. Well, this is the end of this third video. For the next lesson, we are going to be talking about the experimental semivariogram, about the parameters, anisotropy, trend removal, semivariogram, and also about the semivariogram cloud, omnidirectional semivariogram, directional semivariogram, and variance map. Thank you very much for watching this video and see you on the next one.